Good afternoon, students. As we are studying chapter thermodynamics, and yesterday we had the topics as we were studying about the system and surroundings, and left of the portion of yesterday's topic. Today we will discuss about that, and that is internal energy. That is internal energy and change in internal energy. That's a topic which has been remained yesterday's topic. Today we will finish it. After that we will study the first law of thermodynamics, which is very important. So every substance have a certain amount of energy which is called internal energy. It is denoted by capital U. Okay, so internal energy is denoted by capital U. It depends on it depends upon the nature and condition of temperature and pressure. So it depends on nature, temperature and pressure. Example, the internal energy or capital U of 1 mole of water is different at the temperature of 280 Kelvin and 290 Kelvin. So at the different temperature, the internal energy will be different. Okay, so change in internal energy. What is change in internal energy? So it is denoted by del U. Okay, it is the difference in the internal energies of the products and the reactants involved in the reaction reactions. So internal energy changed in internal energy del U is equal to U, so internal energy of the products minus internal energy of reactants, or we can write del U equal to U P minus U R. That's the equation of internal energy. The value of del U is positive if product side is greater than the reactant side, and will be negative if the reactant side is greater than the product side. So here is difference both of internal energy. So we can say del U is equal to heat energy exchanged between the system and surrounding at constant temperature and volume, which is denoted by small q and v. So that's the remaining topic of yesterday's. Now the topic is first law of thermodynamics. First law of thermodynamics. Okay, or law of conservation of energy also. So as we are dealing with the energy changes, so it is important to remember energy may change from one form to another form, but the sum total of energy of the system and surrounding always remains constant. Okay, it is important to remember that. I am repeating here. So the energy may change from one form to another form, but the sum of total energy of the system and surrounding always remain constant. Always remain constant. Okay, so the generalization has been summed up by the Helmholtz in the form of law of conservation energy. So different statements are taken here. So directly we are going to represent the mathematical representation of the first law of thermodynamics. So mathematical representation is important of this first law of the thermodynamics. So मान लीजिए आपके पास, let's suppose that a system has internal energy. Let's suppose that a system has internal energy equal to U1, as suppose if it absorbs heat energy Q, okay, from the surroundings, so its internal energy will increase and become we have U1 plus Q after adding U1 plus Q. Okay. Now for the next term, if the work if the work W is done on the system, then its final energy will be U1 plus Q plus W. Okay, for the work. Now let it be U2, because altogether, as we have formed this equation for the 1, as we have internal energy equal to U1. Now for the U2, okay, let it be U2. So U2 equal to U1 plus Q plus W, or U2 minus U1, or del U will be Q plus W. Okay, because here is change between the internal energy, which is denoted by U. So change in internal energy, which is denoted by del U, is equal to Q plus W. Q, you know, the heat energy, and W is the work. So the final is change in internal energy, equal to heat energy plus work, as above equation mentioned here. In case W is the work done by the system, then change in internal energy will be heat energy minus W, or Q equal to del U plus W. Okay, in case of the W is the work done by the system. Here is most important thing in this topic, or the first law of the thermodynamics. It is the sign convention for heat and work, which is very important to detect the sign. So I am forming here. It may be noted there the sign of W and Q are related to the change in internal energy. You know very well the sign of W for the work and heat energy for Q are related to the change in internal energy del U. So generally we are writing and forming some equations. Q from statements. Q, heat energy is positive or will be the positive if the system absorb energy from surrounding. Okay, if system absorb the energy from surrounding, so the heat energy will be positive. Next equation, heat energy is negative if system releases energy to surroundings W for the work is positive if work is done on system and work is negative if work is done by system. Here is different between the system. Done on system will be positive and done by the system will be negative work. So that's the first law of the thermodynamics. Internal energy also be denoted as E. Internal energy of a substance can also be denoted as E and change in internal energy as del E. That's the first law of thermodynamics. Okay, we have a question related to thermodynamics. As I am writing here an example. A system, if a system absorbs 400 joule of heat and does work of 40 joule on surroundings. So calculate the change in internal energy. Okay, so this is the question. System absorbs 400 joule of heat and does work of 40 joule on surroundings. So calculate the energy change in internal energy. So how can we solve this problem? So here is absorb. So firstly we need heat absorbed by the system. Okay, so system absorb heat. So this is our Q equal to आपका हो गया 400 joule and the work done by the system, it is by the system, so work is done by the system is negative. Okay, that's a clear. So you know how is important these terms. So W is equal to minus 40 joule. Okay, now the first law of the thermodynamics, we have equation change in internal energy del U equal to Q plus W. Okay, so according to the first law of thermodynamics, so putting the value of a Q, we have 400 and we have minus 40 because plus minus minus, so we have remaining the value is 350 joule. So that's the answer, 350 joule. So this question will be solved like this. Okay, so as much this question will be solved. Now the topic is going on further and further. We have the next topic is change in enthalpy. Change in enthalpy. Okay, so we have the new page for the change in enthalpy. So change in enthalpy. Change in enthalpy. Change in enthalpy change in enthalpy del H is the heat energy exchanged between between the system and surrounding at constant temperature and pressure. Okay, denoted by QP. So del H, change in enthalpy, del H equal to QP. Okay, so let's move further. Mathematically, how can we is a low brightness of this mobile phone, so it's good. So mathematically, how can we write it? So del H, you know, enthalpy for the products minus enthalpy for the reactants. Okay, so enthalpy for the reactant will be H, or enthalpy for the product minus enthalpy for reactant, denoted as like this. So the value of del H, the value of del H will be positive if product side is greater than the reactant side, and the value of del H will be negative if product side is lower than the reactor side. Okay, in exothermic reaction, system loses energy to surroundings. So both heat energy and pressure and enthalpy are negative. Okay, in endothermic reaction, it will be positive. That's the relationship between del H and del U. So here is relationship between del H and del U. It is important, the relationship. So in obtain the relation between del H and del U, so we have a equation or reaction A converted into B, general equation. So let heat energy for A be the enthalpy of the reactants and B for the products. So you know heat equal to energy, internal energy, pressure and volume. Okay, so for reactants equal to internal energy for the reactant plus volume of the reactant, and for B will be internal energy of the product and pressure for the product also. So del change in heat energy will be P product minus reactant equal to product plus PV for the product minus reactant A plus PVA. That's the final equation. Product minus reactant energy plus pressure volume of the product minus and a pressure and volume of the reactant will be del U plus P del V. That's the final. So the sum of change in internal energy and energy as pressure, volume, work. It will be further, but here is something. So move further. The relation has been expressed in another form by making use of ideal gas equation. So according to this equation, PV equal to nRT. This is the gaseous equation. Now for the reactants, we have PVR equal to nRT, and for products it will be PV P for NPRT. So VR and NR from both equations, VR and NR, the volume and moles of reactants, okay, and VP and NP stand for the volume and moles of products, okay. So subtracting we have product side minus volume of the reactant side will be moles of the product into RT minus moles of the reactant into RT. Having common of the pressure will be product of the volume, and volume of the reactant will be moles of the product and moles of the reactant into RT, or P pressure and change in volume will be equal to del RT. Substituting the value of P delta V in the relation, so we get del H equal to del U plus del RT, okay, where del H, change in enthalpy, and del U change in internal energy, and del, as you have mentioned here, small ng, number of gaseous product moles minus number of gaseous reactant moles, and T is equal to Kelvin temperature and R is gaseous constant. That's the final equation. Change in enthalpy. So that's all for the today's topic.